Hello, welcome to the Blue Hour. I am Farah Guerrero. Before we begin, I would like to acknowledge that I'm speaking to you here live from the traditional, ancestral, and unceded territory of the Musqueam people at the University of British Columbia in Vancouver, Canada. As we enter a conversation about nature and the deep structures of the universe, this acknowledgement is also a reminder that knowledge is always spoken from somewhere, from a place and from a history. On today's show, I am very honored to be speaking with Professor Philip Stamp. Professor Stamp is a professor of theoretical physics at the University of British Columbia and director of the Pacific Institute of Theoretical Physics, known as PITP, which he returned to Canada to establish in 2002. Mostly raised in New Zealand and educated in the United Kingdom, Professor Stamp began his academic life in philosophy and literature before turning to theoretical physics. He has since worked across many countries, including France, Spain, New Zealand, and the Netherlands, Japan, Canada, and the United States. His research explores many aspects of quantum mechanics, including macroscopic quantum phenomena, quantum gravity, and quantum cosmology. Recently, his work with collaborators on superfluid helium and quantum vacuum tunneling received attention in many science news outlets. The research uses an ultra-thin film of superfluid helium to model the Schwinger effect, a famous prediction that under extreme conditions the quantum vacuum may produce particle-antiparticle pairs. And in this work, this idea is approached through vortex and anti-vortex pairs emerging in a quantum liquid. And so today we will be speaking about exactly this, about this quantum vacuum, superfluid helium, quantum tunneling. And Professor Stamp, I am sure, will make this very easy for us to understand. And he will, I hope, talk about the strange beauty of a universe that, in his words, is both magical and real. Thank you for joining me today on the Blue Hour.
Thank you.
Now, last spring, you delivered a lecture at the Vancouver Public Library, and I think it might be a nice place to start. And I did mention that I had a philosopher who you know, Professor Dr. Paul Bartha, here at UBC, who studies analogical reasoning, and you also talk about a lot of analogs in your research, and you certainly understand them, but they are connected. So I like how philosophy was something you started with, he started with math, and then you sort of interchange paths, but there's a connection, and I really like that. But in this talk, it's titled From Quantum Cosmos to Quantum Computers, the Sacred and the Profane. Can you bring us back to the Vancouver Public Library when you delivered that lecture and tell us a little bit about what you said?
Sure. Well, the talk was not aimed at scientists, although there were people there who were interested in science. As far as I know, there wasn't a single scientist in the audience of several hundred people. In fact, I was partially aiming it towards people I know in the flamenco community in Vancouver, and had long discussions with them about it before I gave the talk, about what is sacred and why we think it's sacred. The profane came later, and I actually never had much time to get onto the profane in the talk. But the things that I discussed as being sacred included things like the truth, which I believe has a sacred quality. But I used as an example of artistic endeavor flamenco. And this is something that people in flamenco talk about. They may not use the word sacred. They use other words, one of the best known being duende, which is an interesting idea, sometimes described as a inspiration, but also as a feeling that you've been taken over by something that's beyond yourself, that's more than you are, and which, when it fuses musicians, dancers, singers together, produces a really unique experience. So it involves creativity, it involves something greater than yourself. Now, scientists, particularly in theoretical physics, have had similar feelings, and so I discussed some of that. Einstein made lots of pronouncements about it, and Einstein's always good for quotes, and so I gave a few. But I think the most important thing that I tried to emphasize was that Einstein created a large number of interesting theoretical structures, but the most important is what's called general relativity, and the whole of physics, and actually basically the whole of science, stands on two edifices. One is quantum mechanics and the other is general relativity. Essentially all of science is based on these. And the incredible thing is that he created the theory, and yet its predictions were almost wholly unexpected for him. And in fact, he didn't believe almost any of them. And they all, of course, turned out to be true. And the idea here is that there's something that we can create, which is much greater than ourselves. And there's no question that that's what Einstein felt. It's what he felt about the universe. It's what he felt about what we could discover about the universe. And so I tried to draw parallels between this feeling, if you like, that there's something sacred about the universe and what we can find out about it, and the feeling in flamenco that there's sacred things about flamenco, which, in my view, are not so far away. Now, it was very interesting because the people I talked about this with in the flamenco community had very widely differing views on it. So some of them felt that, for example, that the term duende is something you cannot use outside of flamenco, and other people felt the exact opposite. Luckily, I was able to find an interview done with the person who is certainly the greatest guitarist of the 20th century, who was a flamenco guitarist, but he also played jazz. This is Paco de Lucia. Wow. And it was the only interview that I think that he ever gave in English, where he talks about duende, and he makes it utterly clear. It's very funny what he said. He said, duende is everywhere, and it can be found by almost anyone, in almost any situation. He said, for example, it could even be found in an interview, but not in this one. But he, of course, was somebody who, just like Einstein, was never satisfied with what he did. Mm-hmm. He always felt that he was trying to attain something that was for him unattainable. Yeah. And Einstein felt the same. And they were both grasping for this thing which was sacred.
This is absolutely beautiful. I had not expected to arrive here at the CITR studio beginning with flamenco. And I am one of these people that, for the first time last year, started to learn the dance. And so I know just a little bit about it. And it is really interesting to, to imagine that you are now bringing something that is very old and certainly has very long histories that traverse, that go beyond the borders of Spain, certainly.
Oh, yeah, it's 800 years.
Absolutely. And to bring it into this quantum world, that's absolutely fascinating. And I do know about Paco Lucia, and I've watched him, and he was extraordinary. So
who are you learning from?
Well, Maria is her name, but I haven't taken a class in a while, but it was last fall. Okay. I was coming from Whistler to Vancouver once a week, and you'll inspire me to go back to that. But how wonderful is that? So just very curiously, did you have flamenco dancers at that talk? And now how do your fellow scientists think about this kind of analogy of
there were fewer scientists at the talk than there were people.
But when you talk to your fellow scientists about flamenco, how do they respond to that?
Oh, they think it's interesting to watch.
Yeah. Well, it's certainly complex, very complex, but I like it because there is something you say. I mean, there's a lot that you say. You even compare the universe to a heart, the pulsing heart, but there is that pulsing in flamenco. There is that energy and there's the synergy, and then there is that absolute, like jazz music, it is very spontaneous and it's and yet chaotic in some many ways. So it has that aspects of the universe.
Yeah, but I don't think that analogy works. I'm very deeply suspicious of analogies. People use them. Sometimes they work, but most of the time they don't. And then people get misled by them. And there are very famous examples.
But you do say, though, something about the heart, though, right? The universe?
Yeah, but that's not by analogy with flamenco.
Okay.
No. This is a work I've done. It's mostly been done by a Chinese collaborator of mine. And I'll very briefly describe it. The standard model, if you like, of cosmology involves what's called the Big Bang, according to which the universe began as a point and very rapidly expanded from there. So we say that it began as a singularity, so where space-time basically collapsed down to nothing and became the curvature of space-time became infinite and so on. And we were looking at this and we realized, I'll try and be as simple as possible, that there was a crucial element missing from. So roughly 60 years ago, a group of Soviet theorists produced an analysis of what space-time should look like around a singularity, and it turned out to be far more complicated than anyone had thought. Space-time can stretch in different directions, so that in the same way that you could stretch a rubber film so that it's stretched in one direction and collapses in another, we say that you shear space-time in the same. Shear as a word just means, so if you take a piece of rubber and you shear it, you bend it so that there's a twist and so forth. Anyway, so space-time can do this. This was one of the results of Einstein's work. But as you approach singularity, it's the space-time tends to oscillate, and it'll stretch in one direction, then another, in this wild and chaotic way. And it does this an infinite number of times as you approach the singularity, and it does it more and more violently. This is what they discovered. So a far more complicated picture than what people had thought. What we realized, what we discussed in this paper, is that there were quantum effects that had not been included in all of this, and when you put them in, you actually never reach the singularity. The space-time rebounds and starts expanding again. And so, in other words, there is no Big Bang. And according to this, the universe should oscillate, expand, contract, and so forth, over and over again. But it does it in this random way. So the expansion and contraction is like a heart, but the oscillations are going, the random oscillations that occur as you go in and out are like fibrillation. So when a heart fibrillates, the chaotic electrical signals cause it to sort of wobble as it's expanding and contracting. And if that gets too serious, then the heart stops behaving properly. So that's why I call it the fibrillating universe. I was just, looking for a picturesque
you don't
phrase.
like an analogy.
But it's got nothing whatsoever to do with flamenco.
However, I am a writer, and I do like making analogies and connecting dots. In a lecture where you have something like sacred values and flamenco and heart, I can't help making those connections. Anyway, let's put that aside, because you do use an analog system, right? I mean, that is very much part of your recent research, and we could go straight into that now.
Sure.
I think because this recent research of yours certainly got a lot of traction last fall, if I'm not mistaken, and this is really something that, so maybe you can first define what the Schwinger effect is, but this is about a 70-year-old, years
Right.
later, you and your researchers discover something quite extraordinary. So why don't we begin with that?
Sure.
And what did Julian Schwinger predict in
Well,
1951?
let me back up and say the real question is, what is the vacuum?
Okay, well,
so-
sure, you can ask the question.
Yeah. So we think we know what a vacuum is. It's something that's utterly empty. There's nothing there. And in fact, for most of human history, that's what people thought. Well, if you look out into the sky, there's something that was noticed a long time ago, which is that it's basically black at night. And this tells you something incredibly important about the universe. Not only that it's almost completely empty, but that it's only existed for a finite period of time in its present form. But it really is empty. The mean density of the universe is basically 1 hydrogen atom per 10 cubic meters. So that's very, very empty indeed. The Earth's atmosphere is roughly 10 to the power 30 times more dense than that. So space is very, very big, but it's also really empty. That's why we can see all the way back, because light just travels all the way from wherever it was emitted 15 billion years ago to us without being disturbed by anything on the way. The vacuum seems to be simple. It seems to be just nothing, emptiness. So the first discovery that showed that couldn't be right was that of Einstein. He showed that the vacuum, in fact, space-time, can have all these properties. It can be curved, twisted, and so forth, and that curvature and that twisting carries energy, huge amounts of energy, in fact. So the vacuum is not structureless, even though it looks like it. It has all these properties which we describe, using ordinary language as stretching and twisting and so forth. These are just words which describe the mathematics. So that was the first notion, that the vacuum was not simple. The second was the discovery of quantum mechanics, and we discovered that the vacuum is something that you can excite, that if you kick it hard enough, you'll produce particles. But kicking it hard enough means really kicking it hard. What Schwinger discovered, theoretically, it's never been seen, was that if you applied an incredibly strong electric field to the vacuum, it would become unstable, and a profusion of particles would appear, and they would just go on without limit. So the vacuum would seem to be disgorging without limit these particles, which are electrons and positrons. Now, the reason it's never been seen is because the fields required to do that are just colossal, way beyond our capacity to produce on Earth. But it tells you now that the vacuum is a bit like some featureless sea. You look at it, there seems to be nothing going on. Maybe if there was a bit of wind, you'd see a few waves, but that's it. But it turns out that underneath, there's all sorts of things going on. And the only way we can see that is by disturbing it in some way. So the vacuum is not simple. Well, this had never been seen. Actually, we were thinking about something totally different, which was if you have a current flowing through a two-dimensional superfluid, we expected something interesting to happen. A superfluid is a fluid which has no resistance to flow and has other interesting properties, but that's the one that counts here. So if I start a superfluid moving, it'll simply go on forever. I mean, and I really mean forever, if you're at zero temperature, until it flows too fast. And then all of a sudden, these so-called quantized vortices will appear, and they'll actually slow the flow. So they'll appear out of nothing, and they'll appear in pairs. There'll be one vortex spinning one way with fluid flowing around it, say, clockwise, and the other one will be an anti-vortex with fluid going around it anti-clockwise. And these will slowly pull apart, and they'll be pulled apart by the flow. So we worked all of this out.
So like almost like whirlpools? Was that a
Yeah, a
good
vortex
analogy?
is like a little whirlpool, yeah. So you've got two whirlpools which are spinning oppositely. So if you pull them apart, the total amount of, if you like, circular flow is not changed because they cancel each other out. But if you're near only one of them, you see a whirlpool, a vortex. So we predicted theoretically that this could happen at zero temperature by a process called quantum tunneling. And it was at that point I thought, well, this is interesting. It's analogous to the Schwinger effect. So here's this magic word analogy that you mentioned at the beginning. So what does analogous to mean? It certainly doesn't mean identical to. So the question is, how good is the analogy? Is it one that's fruitful? Or are you going to find that it breaks down at some point? So there have been analogies in physics that have been just wrong. So, for example, for centuries, people believed that light traveling through empty space was like sound traveling through water. It was something moving in a medium. And so they talked about the ether. So the ether was something that people believed in for centuries. And then Einstein came along and said, no, there's no such thing. That this analogy is just wrong. And people can be misled by analogies and get into all sorts of trouble. So that's why I'm suspicious of analogies. But this analogy turns out to be pretty good. And you mentioned that there was a lot of press about that paper. They all focused on the analogy. That's all they were interested in the science press, the fact that it looked like the Schwinger effect, which is a famous effect because Schwinger made this prediction, and it was kind of extraordinary that the vacuum was unstable, and he made it at the very beginning of our understanding of quantum electrodynamics, which was a huge revolution in physics in the middle of the last century. And so the press climbed onto that, and in my view, they kind of missed some of what was really interesting about it, which was the superfluid part of it, which is the real system we're talking about. So I think that truth is sacred, but so is reality. Analogies are one thing, but there is something real that you have to focus on.
And that's, I think, why you use the word truth. Now, I'm curious if we can just break this down a little bit, because this is a paper that you, as far as I understand, you've done the math, to predict it's still it's theoretical, but you do believe that this could be an experiment that can actually happen. And so why don't we break this? So in your model, this two-dimensional superfluid helium film serves as an analog of the quantum vacuum, as you've explained. And so can you break it down? If we were to imagine this as an actual experiment, what would it look like?
So people would take the simplest experiment. Doesn't mean it's the easiest to do, but it's the simplest to imagine, would be you would have some flat piece of, say, graphite or something that can be made completely flat, and you would have superfluid helium-4 flowing over it, and then you would look to see what happened as you increase the flow rate. And there are ways that you can detect these vortices, these whirlpools. They're very, very small, but you can detect them in different ways, and you basically watch to see what happens. And the prediction is that as you reach a certain flow velocity, the vortices, or the vortex-anti-vortex pairs, will start to be produced, and they'll be produced at a very specific rate, which is calculated. And that rate can be varied by varying the flow velocity. But the key point is that this would happen at very low temperatures. So the only way it can happen is through what's called quantum tunneling. Exactly. It's a completely quantum process. Mm-hmm. So that's the simple experiment that could be done, except it's actually a very hard experiment to do because observing the vortices is very hard. There are other ways that one could do it. For example, with so-called superconducting films. So superconductors are like superfluids, except that it's electrons that are flowing, and systems can be made superconducting at a much higher temperature than the superfluids. So it makes the experiments much easier to do. And it's also much easier to see superconducting vortices because they carry a magnetic field, which is easy to see. So it might be that the experiment ends up being done on superconducting films. The way it works is theorists use what we understand about nature, theoretically, to make predictions. And then experiments are done to check it out. And if it all works, everybody goes home happy. If it doesn't work, it might even be better, because that means you found that there's something wrong with, or you can have a situation, as occurred with Einstein, where he produced a theory whose predictions were so shocking that he didn't even believe them himself, and yet they all turned out to be true. Then you know that you've gotten a tiger by the tail, and you know that you've somehow probed very, very deeply into the truth about nature. Einstein used himself to talk about, he was always very modest about what he did. He said, I think I've pulled back a little bit of the veil, by which he meant the veil hiding reality. He, like the Greek philosophers, was in no doubt that what we experience is not reality, that we infer the reality, but that we don't experience it directly. So he felt that it was extremely difficult to pull back the veil, but with general relativity, he did it, and he got far more than he bargained for. The kind of theory we're doing is nowhere near at that level. We're just basically using what we understand about superfluids to make predictions about how they would behave in these flowing films, and then realize that there's this very interesting analogy with the Schwinger process. People are never going to be able to see the Schwinger process in a lab. But if the analogy works, they'll be looking at a surrogate system where they can investigate the something that ought to be like it. So in that case, the analogy can be useful if it's correct.
Do you see this experiment in your mind's eye actually being seen? I mean, So that's driving you. How close are you to that? And where would that?
Well, I'm not going to do the experiment.
Exactly, but who would, and where would it take place? And I would imagine, like, is there? Do you need to have very cold temperatures? Right? There's not. It's not. So, you've got to create the environment for that experiment.
Yeah. So there are a number of places where I could imagine it being done. One of them is Brisbane in Australia, but there are other places. And you never know who's going to look at a paper like this and say, "Oh, that's an experiment I could do," and it might be somebody you've never heard of. I mean, so. And in principle, there are lots of labs in the world that could do it, but it will be a difficult experiment, and you just put your finger on why. It will need quite low temperatures, and also the problem is to see the vortices in the superfluid. It's very hard. That's why I'm saying that maybe it'll be done with superconducting films, because then you don't have to go to such low temperatures, and it's very much easier to see the vortices. So it's possible that's how it'll be done, and in that case, it could be done pretty much anywhere, because there are so many places in the world that can do experiments on superconducting films. One of the reasons for that is that they're important for technology. So lots of people look at them without any thought of testing anything fundamental. They're just interested in making devices of some sort. So, I mean, that's a huge industry across the world. So who knows who would do an experiment like that?
And even helium, if you remember during the recent sort of Middle East crisis, what we've seen with Qatar, that Hormuz Strait, the helium was something in the news because we wanted to make sure that was still able. We're still the world could receive it, and especially for people that do this type of scientific laboratory research.
I don't know if you're interested in why that's so important.
I would love if you could answer that, yeah.
So helium for a long time came from two sources. Coal mines, very deep down, because the gas was produced by radioactive decay, and deep down in the earth had nowhere to go. So people, for example, in Poland would dig these deep mines and they would find quite a lot of helium, and they were sensible enough to capture it and store it, and then, of course, sell it. And the other source was basically the fabrication of nuclear weapons and to a much lesser extent in nuclear reactors. Well, the nuclear weapons sources basically dried up, and the coal mines, people aren't mining coal so much these days. Yeah. So the helium supply in the world is kind of disappearing. Yeah. And if you want to go to very low temperatures, you have to have helium. Mm-hmm. So it's become more expensive. I mean, when I was a graduate student, we used to say that a container of liquid helium-4 cost about as much as an equivalent quantity of beer. But now it's far more expensive than whiskey. So.
Wow. I'm actually going to be speaking with someone you may know as well from the Sauder School of Business, Dr. Werner Antweiler. He has a background in energy and trade, and so this may even come up. As you can see, I like to connect the dots all the time. But let's just go back to the tunneling again, because this is so important. This just to give us sort of a visual. So if I understand correctly, it's quantum tunneling is a kind of system that passes through an energy barrier that in ordinary classical physics it should not be able to cross. So can you give us kind of like how can we imagine what this quantum tunneling actually is?
Right. So it's always very difficult to describe what quantum tunneling is, because most people don't have in their minds the idea of an energy barrier. It's a scientific concept. Mm-hmm. The French have a word for quantum tunneling. They call it l'effet passe-muraille, which means the going through the wall effect. Oh. So they imagine that something is on one side of a wall and then it appears on the other side, mm-hmm. having gone through, and yet the wall is still there. So how did it get through? Mm-hmm. So it seems completely counterintuitive. And yet that's what happens in tunneling. You have some physical system which is contained, which is held back by some force such that it should never be able to get away, or which is so confined in some region with a potential barrier around it, like a wall. And nevertheless it does. And the reason that can happen in quantum mechanics is because it's not meaningful in quantum mechanics to say that a specific physical system is in a specific state. So this is perhaps the most fundamental thing about quantum mechanics, is that any physical system can exist in what's called a superposition of states. In other words, it exists in more than one state at a given time. So you can imagine that normally we talk about tossing a coin and it either produces heads or tails. In quantum mechanics, it can be in a superposition of both. Mm-hmm. The most dramatic example of this is the so-called Schrodinger's cat paradox, where you engineer a state in which a cat is simultaneously alive and dead. And Schrodinger, who was one of the founders of quantum mechanics, used this to show how counterintuitive it was. Mm-hmm. If a system can exist in more than one state at a time, it can, if you like, oscillate between them, or it can pass from one to the other, and that's what happens in quantum tunneling.
Now, this is this is interesting material. I have to ask you at this point, what brought you in? Because I didn't address that at the beginning, from something like philosophy, literature, and then of course to this quantum electrodynamics and quantum,
right.
Physics. Like how did you get here? What is your? Because you've been all over the world. what really keeps pulling you in this direction as you go forward?
I guess it began at a very young age. When I was a kid in New Zealand, when I wasn't, climbing trees or running around outside, I would either be reading books or, I read a lot of books, and they were either novels or they were about science. Mm-hmm. And so I grew up being fascinated both by literature, stories, and by science. And so I guess I would have been set for either a career in literature or in science. But then I discovered philosophy at the age of 14, and it was kind of a revelation to me. Mm-hmm. It was basically by reading Bertrand Russell. Mm-hmm. That's how it started. And so after that, I thought, well, this is what I want to do. And so I went to university to do that, and there was this really nice degree being offered in philosophy and literature, so I decided to do that. But I got fed up with the philosophy in the university that I was studying at. So one day I just walked over to the science faculties and said, well, what have you got? And I ended up switching to physics and mathematics in the end. So I did both, and I've never regretted that, because I discovered that you can always read books and think about literature, and you can always think about philosophy, but it's very, very, very hard to do theoretical physics if you hadn't had some sort of training. It's just so technical. And that you have to acquire.
It's quite the skill set.
Yeah, almost nobody has ever succeeded in doing that without having,
yes,
gone through a university degree. I mean, I can only think of one person, and so.
Now, when you speak to people that may not know anything about quantum physics, what do you feel draws them in? Because I have actually just the other day, after rock climbing, I was driving back with these climbing partners, and one of them was saying that they really like quantum physics, and I was asking why, because I'd mentioned I was going to be speaking with you, and he said he's just fascinated by the possibilities of trying to understand the origins of our universe. So, is that generally what people are drawn to? I was also in CERN
Yes.
I brought my teenage son he was a young son at that time, maybe 11 years old. And he, we planned a trip around his love of physics, and we ended up in Geneva. We didn't get to go underground. It wasn't open, but we were certainly at CERN and then also Triumph here at UBC. So what is really what pulls people into this?
I think different people have completely different reasons.
And they're all backgrounds. Would you agree on that?
Well, most people who go into, say, physics or indeed any science will have had an interest in it when they were young, I think. I mean, not all, but most.
But in the general population, why are people interested in quantum physics?
Oh, God. I used to teach a class once to students in the arts faculty it was actually about the history of physics. And I would always ask them at the very beginning, why are you taking this course? And usually it was because they'd read some article in the popular science press or read a book or whatever, and it sounded really cool. But unfortunately, these articles are almost always about the kind of more far-fetched areas of physics, fantasies and string theory and so forth. Mm-hmm. And somehow they thought this was the most important thing. Mm-hmm. And I always would say to them, look, just look at the world around you. Everything that you see is fascinating. And understanding that is going to give you an incredible appreciation for the beauty of nature. Whereas all of these fantasies that are cooked up, most of them, virtually all of them, are just that, fantasies. The fantasies of string theory, for example. There's absolutely no experimental evidence for them. There never has been. And frankly, I don't think there ever will be. And yet this is what tends to attract a lot of people in the public. And it's because they watch kind of gee whiz stuff on YouTube or on TV. And it's unfortunate, because the real world is so much more interesting and fascinating.
I have heard about the rift between quantum physicists, and you just mentioned the string theorists have, unfortunately.
Well, they're kind of notorious because they've made such ludicrously overblown claims, you see. So they kind of make themselves a victim. They make themselves a target,
Now, one of my favorite quantum physicists is a man named Carlo Rovelli, who one day when I was in Marseille, in France, I knew he had worked there, and I had this imagination that I'd maybe knock on his office door and he'd open it up and I'd be able to talk to the man. And I had found his first book. It was very similar to what you said about teaching an arts course. He writes this book that's really an introductory book to physics, really. And it's just essays that for someone like me who didn't have a science background, it was very useful. And that's how I entered that kind of quantum world. And he's also a writer.
Yes.
Do you have his personal contact information? Can I get him on my show?
Yeah, I know. Well, he actually spent a short time in Eastern
Canada.
Yeah.
During the pandemic.
Yes, exactly.
In Ontario.
Yeah.
Yeah.
But I, as far as I know, he's gone back to France. Yeah. Well, of course, Carlo works in quantum gravity, which is rather distant from,
quantum physics still, right? Mm-hmm.
Well, I mean, look, everything is quantum. So quantum mechanics supposedly applies to everything in the universe, although, there are very interesting and good arguments for why it should not apply to massive objects, but that's another story. Honestly, when I was young, it wasn't that kind of book that fascinated me. I wasn't really interested in books that used the crutch of metaphor and analogy to explain things. I wanted to hear what it really was. Actually, the books that really converted me to the idea that physics was amazing were the so-called Feynman lectures on physics. These were lectures given to undergraduates at Caltech back in the early 60s, which have now been translated into well over 100 languages, and millions of copies have been sold. And you might ask why? Because they're, this is real physics that he's talking about. It's not destined for a popular audience, but it's because his ability to relate understanding of perfectly ordinary physical phenomena that we experience, all of us, every day, to really deep fundamental aspects of physics was unparalleled. But that's real physics. The idea that we only worry about stuff that may be on the other side of another universe, because Carlo, amongst others, likes to talk about the multiverse, is, to me, just childish. I mean, deal with the real world as it presents itself to you first, before you start fantasizing about other worlds.
Now, is that why you use the word truth?
Yes. Well, it's one of the reasons.
Because you even said just now, I've lost the word, converted. I mean, I'm curious about these words. When it has a sort of religiosity kind of feeling to me, and so I'm curious about if you can maybe define that. I never saw the actual presentation at the Vancouver Public Library, but you did send me one slide, and one of the first things you say is most of us hold certain values to be sacred. One of these, which underlies science, is truth. Yeah.
Right. And I think that's the case. I mean, it's certainly the case for me. I think that truth is hard to get at. I mentioned that before. Humanity has erected a very large structure ideas which they think, at least some of them, are true or approximate the truth. But of course, I mean, there are other ways of thinking that are not scientific or which don't at least claim to address directly reality. So my view of religion is that it's motivated in some ways it's motivated by similar things to science. For example, this feeling of awe about the unknown, no question. Mm-hmm. But unfortunately, most organized religions pretend to understand these deep things, and they don't. I mean, and so I'm always very suspicious of organized religion. But the religious feelings of some people, that's a totally different story.
But you also use the word sacred, so I'm just curious.
The word sacred may
how you're bringing truth sacred.
Yeah, religions may attempt to appropriate the word sacred, but it doesn't belong to them.
But in your view, scientifically, how would you define these words?
So which ones?
Well, sacred. Let's do that one, because you say the sacred. There are non-scientific sacred values: beauty, love, nature, compassion, even comedy. But you are, from what I understand, these are words that mean a lot to you as a scientist.
Yeah, well, if you say that something is sacred, again, that's a word that has many different meanings. Obviously, it's precious. You value it enormously. You believe that it's something that has to be protected and has to be propagated. That is to say, that it should be part of life, insofar as you can make it so. And it's something that typically involves things that are unknowable, I guess, in the way that we usually think about knowing things. So, but which you feel are somehow fundamental to the world being as it is. Now, of course, there's also a moral side to the idea of sacred, that it's somehow good or right. That's where things get a little more difficult, because different people have different ideas about what is right and what is good. And that's why we end up with different religions saying different things, and different people following those religions and then deciding that the other religions are wrong, and therefore those people have to be persecuted or killed, and so on and so on. And I think it's fairly accurate to say that many of the worst conflicts in the world have been fundamentally motivated by different religious views. And so I don't think that... This is why it's so subtle, because something can be sacred, but you should never be dogmatic about it. So if I say that I feel that truth is sacred, that's my view, and I'd be prepared to defend it, but it's not something that one should be dogmatic about, because there are other things that are sacred as well. At least I think everybody has views about what is sacred. Their views, however, are not necessarily the same, and so there has to be a lack of dogma here on the part of different people. So, I mean, this is a long discussion. If you're asking me to give a definition of sacred,
I'm just curious from a perspective of a scientist like you. It did strike me very interesting, and of course, as you started with something like flamenco, it's even the title, From Quantum Cosmos to Quantum Computers, the sacred and the profane. Because I'm a writer, words are loaded with a lot of meaning, I'm very curious.
During my talk, I was able to say a lot more, because I was able to show things, both on slides, and I did some demonstrations, so it's much easier, because of course there are lots of other things that people feel are sacred, and I wouldn't necessarily disagree with them. I mean, love, for example, although what that is So then somebody will say, okay, so what is it that's sacred about love? And then you have to explain what. So this is a long discussion, and you're going to get into a long discussion about almost any of these. So if somebody says, okay, what is truth? Now I'm having to explain what I mean by truth, and truth for most philosophers, particularly Anglo-Saxon philosophers, is something that is a property of statements and their relationship to the real world. But then somebody will come back and say, well, but there are other ways of acquiring true understanding than through words, through descriptions. So then you start getting into a very lengthy philosophical discussion about what you mean by truth. And logicians will give you one answer, and French philosophers will give you another, and British philosophers yet another, and so on and so on. So
maybe quantum physicists another.
Well, scientists have a very simple understanding of this. They fall back on experiment. So in the talk, I showed a very short extract from a.
So is that the truth that you mean when something can be proven?
So
scientifically.
Let me finish what I was going to say. You never prove anything with an experiment, nor do you ever disprove anything with an experiment. I mean, this was the mistake that Popper made. You can give evidence for or against a proposition or a theory, but the problem is that observations always come laden with theory, and so any experiment as well. And that more of the theories themselves are rather elastic and open. They're, if you like, open structures. But Feynman made this remark. It was actually to an audience, and it's probably the best simple description of the credo of a scientist. And he said this: if a theory disagrees with experiment, it's wrong. And he said that we can't deny. He said it doesn't matter who you are, doesn't matter what your name is, doesn't matter how famous you are, or how beautiful your theory is. If it disagrees with experiment, it's wrong. And he said that's all there is to it, and that's science. Now, naively, most scientists would probably agree with that. I'm not sure if Rovelli would, because the work that he does is not really linked to experiment, at least most of it. But it's what most scientists believe. The problem is, of course, that you can get experiments disagreeing with each other. And you can find that the theory makes ambiguous predictions, and so on and so on. So it's not necessarily that simple. But, from a naive point of view, that's the faith of scientists, and that's the truth that they believe in. They believe that the truth is given to you, the truth about the world, about nature, is given to you through the medium of experiments. It sounds simple.
But in the end, you're still a theoretical physicist, and you did say that even in this specific research, you won't be necessarily undertaking the experiment, but someone will. But is your goal as a theoretical physicist to really hope that you will, whatever you are producing out in the world or revealing to the world, will lead to that experiment?
So I prefer a theory that makes predictions to theory that simply explains existing experiments, because you're putting your head on the block when you make predictions, and that's been understood by mathematicians for centuries. I mean, the people who invented what we now call probability, Christian Huygens and Pascal, both pointed out that prediction is essential to science, and that probabilistic reasoning is predictive, that it's making predictions about what might be seen. Mm-hmm. And they remarked, both of them, that if you make a prediction which seems outlandish, which nobody can believe, that just violates everybody's understanding, and it turns out to be true, then you have very, very good reason to believe the reasoning that led to that prediction. So they were already pointing out that all of these arguments are probabilistic, mm-hmm. that we can't say that this experiment has been done and therefore it proves that. All we can do is try and assign a probability to the views that we come to on the basis of that experiment. That's it.
Well, I will have to end it there, Professor Stamp. Thank you. We have a show coming up just after us, so I will thank you for your time. I've been speaking, if you've just tuned in, this is the Blue Hour. I'm Farah Guerrero, and I've been speaking with Professor Stamp. He's a professor of theoretical physics at the University of British Columbia here. And we've had a very interesting conversation that took us from flamenco all the way to understanding something quite philosophical as well, trying to get at the idea of what truth might be. And yeah, I thank you for your time. And this episode will be podcasted on CITR.ca. And yeah, thanks again.
Thank you.